Swayam Prabha. Digital India. Educated India.
Now in this 2 class it was easy. We can only learn that fx, which is going to give you the predictive density of p equal to y given x. What happen if we have other than like more than 2 classes, like k classes? Then we have to learn k minus 1 functions. So it will be like this. So that for every y, so if we think that we have these classes y equal to 1 to k minus 1, and for them we thought this log ot ratio will be a linear functions. So this linear function is for y, class y, which is separated from the class 0, and therefore this has parameter wy and w0y. And then this, for this particular class, what will be our density function is this one, this big exponential over. So this will be the functions of this for y class, and denominator will have all the functions. And for but the y equal to 0 class, we will take it is 1 minus sum over all other probability. So how it looks like? So now we have 3 classes, let's see. So this is going to be, we have some things here, and we have some green point here, and then we have some red point here. So it will be the class 0, and this is going to be the class 1, and this is going to be the class 2. So now think about, this is the probability of y equal to y given x. So it will be 0 to 1. So okay, maybe I should not use this thing. This will be for this blue means y equal to 0, and this green is y equal to 1, and this red is y equal to 2, the true y. So now how does density function should look like for blue? So here for up to this it will be 1, and then it will be little less because of this green, there is something, and then it will come to a 0. And what will be this red? So red will be this side, then it will little bit come down, and then it will be 0. And what will be this green curve? It will be 0, and then it will go little up, it will go 0 here, and it will go 1 here, and then again it will go down and it will be 0. So now everywhere you will see that so here it will not reach to 1, because here it has few values for green and red at this point. So the sum over the all probability will be 1. So here at every point the sum over the all 3 curve will be equal to 1, right? So therefore this blue things, the 0 will write it later, maybe this green one, probability of y equal to 1 given x is going to give you some w for 1 of x, and then the probability of py equal to 2 will give you x equal to f of w2 of x, and then these things we can write it as this is just 1 minus these two things. Okay. So this is how. Now for if we have k classes, we will be learning k minus 1 linear function such that will be predicting the class posterior probability of class for all k classes. And then how will be classifying for this multi-class data is that when we will be predicting all fw, and then we will be taking which has the maximum value, that will be the class prediction. So here if we say now g star of x will be given that arg max of y such that if wy of x, where we can assume that this is equal to if w0 of x. This will be your prediction on the test data. So now we'll see one example. When we learn this logistic regression on a moderately tuned C on this iris data, then we get this kind of separating hyperplanes. So these are the linear, and here this side we have the class, the brown class, this is the yellow class place, and this is the blue classes. So do you now will recall this Bayesian rule again? So now I'll ask you some questions like, so it is clear now what is logistic regression? What we are modeling here in logistic regression? What we are learning? What we want to predict? What is the function? We are learning some probability. What is that probability? So what is these things we are learning? These things? These are not the likelihood. Yeah, these are the posterior probability, right? So we are learning the posterior probability directly for the logistic regression. Now do you remember that for the Bayes rule we can write any posterior this probability and the prior, class prior, right? This is proportional, right? So here we actually thought that this is we will be learning a function that is fwx which will be predicting this posterior probability. Okay, now here x and y both are the random variables for us. Something is known and something is unknown. Which is known and which is unknown? X is known and y is unknown. So now see, if we have a and b, both are random variable. What is this? This is a likelihood or a posterior? Tell me. Is a posterior? Who think it is a posterior? Nobody thinks it is a posterior? I raise your hand. Do you think posterior? Good. Is somebody is there who think it is a likelihood? No? I want a vote. Whoever is not putting his hand to the posterior, I think they are thinking it is a likelihood. Is there anything else it can be? Can you say, or somebody said, I cannot say because you did not give me the full information. Is there anybody who wants me ask that question, that I need some more information before I say it is a likelihood or a posterior? You want? It is a posterior. Okay. Okay. Is there anybody who want to ask me some questions about the A and B, and then he will say that he or she will say this is a posterior or likelihood. So you have to think and you have to ask which is hidden and which is given, which is observed and which is hidden. So yes, you have question? Okay. So now I am saying that A is observed and B is hidden. Then it is what? Then it is likelihood. So if when it is the probability of observed by hidden, then we say it is likelihood. And when it is hidden by observed, it is stays posterior. Okay. Now instead of directly doing this thing, can we do something else? So without learning this W, we will be finding again a linear boundary, and where we'll be estimating these two terms. This is the probability of X given Y, and this is the class probability. So when we assume that probability of X given Y, this class dependent density is a Gaussian, it's coming from multivariate Gaussian distribution, then we can estimate the mu and the sigma of that Gaussian distribution given the samples. So we will be estimating the mu and the sigma of that Gaussian distributions, and how we will be estimating this class prior is by just calculating that what is the portion or fraction of the data point has the Y as a label. So when we did that thing, then when we assume that this probability, the class density probability given a class, what is the probability density of the X, and it is a Gaussian. This you know is multivariate Gaussian. This is an expression of this probability density function, and then this log it ratio we can write in this format. This is the simple algebraic calculation you can do. Just you take the log of this, it will come as like this. And this also again, if you think that if I know, if you calculate these things, the mu y dash, the sigma pi y dash, sigma, and then the whole function has, this is a parameter, this is a some constant, sorry, this is a constant, this is some constant, and again this part is some constant, and it is a linear over X. So then it is again the linear function. And you can use that, if you want this log it to be greater than 0 for class Y and less than 0 for class Y dash. And that is why it will be again, you will be learning some linear function over X. So it is not learning, we know that we will estimate this mu and the sigma from the data itself, and then we can have some linear discrimination function. So here we will have some example. So these are the 3 training data sets given, and this black triangle is our test point. So how we will be deciding what is the class it should get. So here if we learn that Gaussian distribution over each samples. So it will look like this, round, 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 and where this point will have for this point, some of this Gaussian distribution has more weight or more probability, and then this will be classification as that class. So you can think about it is just finding that which mean is close by. When for all the classes you have same variance matrix, covariance matrix, then you can just calculate the means of this each classes and find out that which is the closest from this class, and then you will be classifying this point at that class. So for this, if you think that all the probability has same covariance, then it will give this kind of function. This is generally simply you have to calculate the means, and then you have to find out which mean is closest to this. And when you are calculating the covariance matrix, then you have to weight it your distance by that covariance matrix. So have you heard about this Mahalanobis distance? No? Okay. So like you have two things. One is here, it is 0, 100, thousands, 2000s, like this. So this is a point, and here is a point. And here you have 0.0001. Here you have this one is maybe 0.0002. So if you calculate L2 distance of these 2 points, what will be the value here? It is almost near to 2000. Maybe it is, if it is a 2000, or it will be almost kind of, everything is in the middle, and so it will be 1000. This is our Euclidean distance between these 2 points A and B. And if you have some point here C, the Euclidean distance between the AB and AC will be very same. This will be near thousands only, right? Because you will not giving any weightage of this side, this axis. This has so tiny data. But then this is a not, maybe this difference is much, because it is already, your data set is ranged by this to this, and it is already in the half of the distance of between the AB and the AC. So you should give some weightage of this axis also. So what is the good thing is that when you will be calculating, so you will be calculating x1 and x2 square and give some weightage over this x-axis plus y1 minus y2 square, and gives weightage over some y-axis. This, if it is a x-axis and it is a y-axis, this will be called that like kindly weighted Euclidean distance. And so this type of things we can also write it more generally, more in a general form. It is going to give you so this the x transpose mu x minus mu transpose and x minus mu is going to be give you Euclidean distance. Now if you just multiply it with this covariance matrix in between, then if you think here this covariance, this side will be less and this side will be more, so you are actually dividing by this covariance, then it will give more better, sometimes it will be good, give distance calculations which is helpful for machine learning. So this distance calculations is called Mahalanobis distance. So like this also, here we are calculating distance directly from the mean, so that you will be having this the covariance are the uniform, this identity for all the classes. If now the covariance changes from the identity matrix, then maybe the class boundary will be little different. Maybe like this, if the here all the class has the same covariance, but the covariance is not the identity. It has some off diagonal value. Then our class boundaries changes. And for other things, okay. So for LDA, as it is completely depending on the sample set. So how you are estimating your mean and covariance does matter a lot. So that is why if you increase the number of sample, you will be getting maybe the better classifier, because with the more sample you will be having more accurate estimation of your distributions. And another thing is whether your covariance should be uniform, should be identity matrix, or it should be same for all the classes, or it should be the different, and how dense it should be. All this also your assumptions. Depending on your assumptions also, it will be it will be depend on how good it will be your classification or the classifier. So like one example here. This solid line is the base classifier. This is the best classifier we can get, and the dotted line is the LDA. And here when we have less sample, 20 sample, we will be not having it the estimating the mu and the variance correctly. So we will have the different classifier when we use the 200 sample. And under the incorrect assumption is that here actually the Blaise classifier is not a linear classifier. It is a quadratic classifier, but we had assumed it is a linear, so our classifications also changes. Our performance of the classification changes. So now the relations between the logistic regression and the LDA. So what is the relations between them? They both are which kind of classifier? They both are discriminative, okay. Something else, linear classifier. They both draw the linear line or hyperplane between the classes. But who assume more and who assume less? LD assume more than the logistic regression. LD assume that the class density is a Gaussian distribution, and it also assumes that with the sample you can calculate this parameter of your Gaussian distribution accurately. While in Euler we do not assume anything about the distribution, we just want to fit a posterior distributions. So which one is the better one? LDA or logistic regression? If I give you some data and I will ask you to learn a classifier there, which one you will be using? Logistic regression. But logistic regression you have to learn some linear function, where for LDA your computations will be more less, because you can directly find out the covariance and the mean. Did you think about that? Now are you changing your answer?
Between time and the quality of the results. If I want early results, I must do ready, otherwise logistic would work. If I want the quality.
Okay. Okay, so the practically the thing is that both perform almost similar. For I agree with your answer that when you are choosing some model, you have to do some trade-off, like what is important to you, and you have to choose that models. Like there is no such model which is the best for all the category. So every model has a good thing and has a bad thing. So you have to prioritize what you want. But in practice, it turns out that LD and the logistic regressions, if you have the same assumptions, similar assumptions, so in like actually data is linearly separable, and in that case, both the classifier performs similarly. So you will not maybe see much difference between these two things. this is for what? Okay, so have you heard about this law of large number of probability? So when your sample size are coming from any distributions, but when your sample size is large, then the distribution, this joint distributions is going to be the distribution of sum over x is going to be very Gaussian distribution. It will be very similar to the Gaussian distribution. So this is because of that, and when we have lot of samples, then, and it is coming from the some other distribution, this class density, but when we have lot of samples, this minimizations of assuming the Gaussian distributions will be less harmful, because we are minimizing the sum of the loss over all the points. So here I learn the two regression, two classifier here with the same data. Here the black points were our training data, and the red points was the validation set or the test set. And I see that both the cases, though the classifier looks little different, but when I test with the test data set, both are giving the same test accuracy. Okay. So the takeaway message for this one is what is the classifier and how it is different from the regression and why it is an important task. Do you know why it is an important task? So in reality, in the real world cases, most of the time we do some categorical divisions or classifications of the data. We want tomorrow will be rainy or cloudy or sunny. We want that whether some drug will be effective on some disease or not. And also another important things where we use the classifier is that you are doing some transaction, some financial transaction, and there will be a classifier will detect that whether this is a fraud transaction or not. So in the real world we use a lot of such classification tasks. Okay, so we end here, and if you have any question, any feedback, if you have anything, if you want to meet me now, you can meet offline, or this is my email ID. You can also mail me.